in this prototype, we want to implement 2 automated players that play against each other until one of them wins. And I think, for the most part, that is actually pretty straightforward from what we have. The only one trick here is that the stopping condition of the game has changed very slightly, and that there's not one board, but multiple boards. So if we start from our previous code, I think that we don't really need to do a whole lot in order to get this working. I think we need to see if the code that we wrote before really matches up to what it is that we need in order to implement the automated game. But I guess if we have board A and board B, and we generate 2 boards, and I guess here this is where, hard coding the positions is going to be a little bit tricky because both of the boards are going to look the same, but still I think we will find that it won't really meaningfully change the quality of our results. And here we need to figure out how to change this main loop to run until both boards. So I guess we have result A and result B for the 2 players. And we can say while board A has active ships and board B has active ships. Okay, that's good. Then A's shot is A's strategy. So I guess we need to have 2 strategies. And here we're going to see a little bit of the dynamic of this thing. Strategy B is based off of A's board, and strategy A is based off of B's board. So here we go like this. And I guess the players play in turn. So we'll need something like this. And this is based off of A's result and B's result. And then here we can compute them. A's result is what happens when B's board is struck. And I guess we don't need the shot anymore, so here we don't need to actually name those separately. And then here, I believe this seems to mostly work. So this is a pretty good indication that the original code that we wrote was pretty good. And you can see these printout. We just put these printouts twice. Now, I am actually, and I guess we don't even need 2 results. No, we do need to store the results, so we'll have to do, we might just do something really quick and dirty here. There we go. So, and we'll just notate which player. This is player A, and this is player B. And we'll see if the game actually plays. And you can see, yeah, they missed, they missed, they missed. They hit a battleship, they hit a battleship. And we need to probably figure out who won. So then at the end, it's actually pretty easy. If we can say if there are active ships, basically whoever had active ships won. So we can say A won. Otherwise, B won. Or I guess it's not really possible since it's turn-based. They could have both lost. But we'll just write it like this, just in case. So there we go. So you can see the game's played until A won. Let's change our random seed and see if this looks good to us. Yep. So depending on how they manage to start off with their random strategy, either one wins or the other. So you can see the code that we wrote originally actually worked quite well. Now, we do have a little bit more time to work on this particular prototype. And so one thing we might think is, who's to say that the game of Battleship is just 2 players? Does this generalize to n players? Well, I think it does, because we'd say boards looks like this. Let's say there are 4 players now. The strategies would be each player. So I think what we want to do is we want to have some players. And here I'm just going to represent these as, Alice, Bob, Charlie, and Dana. And here I guess I need to map these. So here I'll map my player to the board, and then my strategies. And I guess if we have a multiplayer game, you get to fire at everybody else's board. So here, this is the player and random fire strategy. And I guess you have to have one random fire strategy for every alternate player. So this is actually something like this. It is a nested dictionary. So this is the board. So let's see. And this thing is the source player and the targeted player. Or here, I'll just call it the I'll call it the opponent maybe. So here for each player in our players, for each opponent in the players minus yourself, like that. Let's see if that works. And this shouldn't be players.keys. This should be, actually we can do it like this. Because the players can be, we consider those to be unique, and that allows us to do the set subtraction. So there we go. And here we need to go through each board. So this would be the boards for that opponent. There we go. Okay, so here we now have a strategy set up for each opponent player. That's good. Then the results would be one per player. So you'd say this is like none, or this is the player mapped to none for each player that you have. So we don't need that. And then what we do is we'd say while all board has active ships. And here, yep, for board in boards.values. That's how far we run for. And then we basically just go through each player. So we say for player and players, you know, the shot is whatever the strategies were for that player. And we have to go for each opponent. And so here, players minus. So for each opponent, this is the strategy for that player for that opponent. For the result, and I guess you need to have the results need to be a map, so they need to be a map for each opponent as well. So here, there we go. So for that, and then you can give this the results for that player for that opponent. Very good. And then I think all we need to do is, yeah, this. And you can see that's the result that we got, and we have to store that result back. So we have to say the result is equal to the boards for that opponent being struck by that shot. And here we'll say this is now the results for that player for that opponent. And we could make that a deck. You know, this is actually a pretty good choice. Instead of having a none value, it's a pretty good choice for like a collections.deck, because we can set a maximum size on this thing and we can always append. So we can keep the entire history of everything that happened in the game, because that might be useful later for reporting purposes, for, you know, replaying the entire state of the game or seeing where something went wrong or even debugging this. So here we can say this would be the last result. And so this would be a deck that is initialized with one value, none. And then here, this should be, let's grab this. And here we're going to say, okay, append the results to this thing. And here, if we were worried about how long this game could run for, we'd do something like max length equals whatever, just to keep that deck from getting too large. And I think that gives us everything that we need. And then, of course, the win condition is pretty straightforward. We just see, again, whose board was which. And let's see what happened here. And, of course, we need to put the player's name here. So put the player here. And let's see if the players actually are, yeah, playing against each other. So this actually works pretty well. It generalizes against everybody. You can see each player gets to fire against everybody else. And what we might do is we might change this condition here so that this plays until there's only one player left. Or here we might say if board.active ships. We might take the board object itself, and we might say if this thing is greater than, actually we can even do something like this, if, you know, there's more than one active player. And so this will play until one person is left. And whoever that one person who's left, they happen to win. And we could even do something like this. We could say active equals, like that. And here, we actually can get the items out of this thing. And I believe this gives us the board, the player and the board. So we could get the player out of this thing, and then we know who the active players are. We're going to get the length out of this thing, and then whoever's left is whoever wins. So I think this should just be whatever, like that. Whoever's left won. So there you go. And So you can see with our game, Bob wins, Alice wins. One problem though, this is very important. Whenever we're using sets, we need to set the Python hash seed. Even though we seeded the random number generator, we didn't seed the hash seed for the sets. And so even though we think this is deterministic, it's not. All of this set here is actually causing this to be non-deterministic. If I change this to a dictionary, or if I change this to a list, then there shouldn't be any sets left, and so it should then always give you the same result. But for now, or if I check the Python hash seed, then it'll fix it in place. But for now, you can see it does bounce around a little bit, so that's going to make it a little bit hard for me to debug. But this seems to work.